All right, let's get going, okay? So, just as a reminder, tomorrow we're going to be doing a little bit of walking because we're going to walk out to the fence in the front. And we're going to decorate it for Pi Day. Start hopefully getting the school a little bit excited for Pi Day. So we're going to do that. I know they're doing the pie in the face thing on Monday, and we will have our own activity in here on Monday. So, what?
Can I bring pie?
I was going to bring pie. I always bring food. I mean, it's Pi Day. We have to celebrate, right? So, I don't know, what kind of pie do we like? Pecan pie? That's tough. Just pecan pie? Nobody else likes anything else? Pumpkin pie? Apple pie? All right. Banana pie? I don't think we can get that many pies. It would be really bad if we ate that many pies. 4 different pies between 11 of us. All right, but I will see what I can do. There will be pie on Monday. We'll just put it that way. Okay. All right. So read the essential question, the I can statement to yourself really quickly. Okay. All right, Carlos, can you read us the essential question?
How do you calculate the derivative of a parametric equation?
Perfect. All right. And Noelle, can you read us the I can statement? Awesome. It would be really nice if we knew what a parametric equation was, wouldn't it? Because we've never seen that before. This is kind of one of the things that even if you had taken pre-calculus here at Tockwitz High School, we would have probably not taught you parametric equations. It's something I pick up usually just in BC. It's not that big of a deal. So we're going to learn a little bit about parametric first. So the first part is kind of a little bit of algebra 2 pre-calculus stuff. And then we will get into, we may or may not get into the calculus piece today. We'll see how it goes. Okay. All right. So what I want you to do, okay, there are a lot of words on this page. Okay. So I'm going to give you like at least 4 minutes. Okay. I want you to read up through this box. So read all of that right there to yourself. Okay. If you read through it once, read through it a second time. All right, I'll give you about 30 seconds, and we're going to talk about all of that. Okay, we're not going to read word for word the first couple of paragraphs outside the blue box, okay? But just some important notes about this. So looking in this paragraph here, is a parametric function, or is a parametric equation a function? No, it would totally fail a vertical line test, right? If you look at what we have there. So it is not a function. The way that we get around that, okay, is it adds a third variable into things, okay? We have an equation for our x, we have an equation for our y, and they are both based on the independent variable of time, okay? And putting those two things together gets us a plots that we can connect together to make our equation, okay? So, and then it makes a path like we have in that little picture right there, okay? So kind of reading through that definition one more time together. So we have f and g are continuous functions, and we are given these two equations. X equals f of t, y equals g of t, okay? They are called parametric equations. T is called the parameter. That's probably important to just understand that vocabulary, that t is the parameter. What it's going to do is it's going to calculate a set of points for us, okay, over an interval. That's what the next sentence says. And then the interval, and that's called the graph of the parametric equation. And then taken together, the parametric equations and the graph are called a plane curve, denoted by C. I don't think they don't have that labeled up there. All right, the important thing that we're going to do, because we're going to practice sketching a parametric curve today, okay? So that paragraph that talks about sketching. When sketching by hand represented by parametric curves, you use increasing values of t, okay? If t is representing time, can it be negative? We wish we had negative time, right? But we don't have we can't go back in time, okay? No negative time. So you start with 0 and you keep increasing your values of time, okay? That means that the curve has a specific direction, and it's called the orientation of the curve. We use arrows to show the orientation, okay? So if I was looking at that curve that was plotted for us, okay, do you see how it has an arrow on it? Typically what we do is we add a couple of little arrows on there to represent the direction that we were going on the curve, okay? So that's part of graphing a parametric equation, is adding orientation on there. All right, so let's try graphing a parametric equation. This really isn't as bad and complicated as it seems, okay? All right, so take like 30 seconds, read that to yourself. Apparently, I take that back. We can't have negative time or negative t values because we have both sides of the graph. So apparently t can be negative. All right. Yeah. Say it one more time.
The other side of the graph be like 4x, not 3x second.
What we do is we're basically calculating our x and our y individually. So we're going to calculate each point and then plot the point and then make the smooth curve out of the points. Does that make sense? Okay. So we use time, and the time adds the orientation piece to the graph, and then we plot the points. That gives us the curve part of the graph. Okay. So bear with me on that example, and if you need to ask the question again, ask it again. Okay. All right, so I'm going to use that x is t squared minus 4 and y is t over 2, okay? It told me my domain for my t, or my interval for my t, is between -2 and 3. So I am basically plugging -2 into both of those, -1, and so on, okay? So all we're doing is filling in the t-chart right now. So when I plug -2 into x, that would be 4 minus 4. What's that going to give me? Good, 0. All right, when I plug -2 into the y equation, what are we going to get? Just 1? -1. What we just created was the point 0, 1. So we're going to plot, 0, out 0, down -1. So that's our first point of our curve. Okay. All right, I'm going to plug in the -1 now. So when I plug -1 into x, what do we get? Good. When we plug -1 into y, what do we get? Good. And then I could plot the point out -3, down 1/2. I know that I'm going that direction on my orientation. I'll connect the curve once I get all the points in there. Okay. All right. We're putting in 0. So when I put 0 into x, what do we get? So put 0, I'm sorry, into t, into the x equation for t. What do we get? -4, right? Okay, when we put 0 into the y, what do we get? 0. Good. Okay, so we're going to go out -4 and up 0. All right, here's what I want you to do. Okay, I want you to fill in the rest of the table. I'm going to give you like a minute and a half, 2 minutes to do that. So fill in the rest of your table. Do the calculations for 1, 2, and 3. Okay, I want you to check with your table and compare your answers. All right, what did we get for 1? -3 and 1/2. Everybody good with that? -3, 1/2. So I'm right here. Okay, what did we get for 2? 0, 1. Good. So we're out 0, up 1. All right, and then what did we get for 3? 3/2, which for graphing purposes, we'd be better at 1.5, right? That's an easier way to see it on the graph. So we're out 5 and up 1.5. Ooh, that's a weird looking point. Let's try that again. Okay, so as far as my graph is concerned, I am now going to plot, or I'm going to make that into a smooth curve. Okay, so I'm going to start with my starting point. This was the first one, and it's important to know what was first. Okay, and you want to connect it in that order. So we're going to connect the curve, and then you want to draw your little arrows on there for your orientation. We know it's going that way. Now, it kind of looks like part of a parabola but laying on its side, right? We do have a rectangular equation for that. Eventually, we're going to get into how to get a rectangular equation, or what we're used to is what we call a rectangular equation versus a parametric. Out of that, we'll see that a little bit later in the lesson, okay? Right now, we're just focusing on how do we get it graphed. What does it look like graphing it? Okay, let's look at the next one. The next one's missing a little bit on the table, but go ahead and really quick read the problem to yourself. Okay, so we've got a slightly different curve. Our x value is sine of pi t over 2, and our y is equals t. Okay. So we're going to have to do some trig work on this one. Doesn't that sound like fun? But there's some things missing in our table. Notice my table only goes 1 to 5. Look at my interval goes from 0 to 6, right? So I really was missing the 0 value on the table and the 6 value on the table. So I'm going to kind of squish those in. Okay, we're going to plug in 0. So when I plug 0 in for sine, all right, so let's go back and think about 0 for sine. Remember that this is out 1 up 0, out -1 up 0, out 0 up 1, and out 0 down 1. Okay, so is sine the x-coordinate or the y-coordinate? The y-coordinate. Okay, so sine of 0 would be here at 0 radians, which is what? 0. Good. And then y equals t. That's nice, isn't it? Can't I just put 0 for that? In fact, could I fill in all of my y values right now? Aren't they going to match my t values? Yeah, so couldn't I just write 1, 2, 3, 4, 5, 6? That was nice. Good thing that part was nice, because the other part isn't as nice. Okay, because we've got to do all this trig. Okay, so I'm going to do a little bit of scratch work to the side. So I'm going to plug a 1 into this guy next, which is going to give me sine of pi over 2. Remember that this is 0 radians, pi over 2 radians, pi radians, 3 pi over 2, and so on. We can keep cycling around. So at pi over 2, what is my sine? What's the y value? The y value. 1. Perfect. All right, I'm going to go into that same x equation, and I'm going to plug in a 2. 2 pi over 2. So now if I simplify that, I have the sine of pi. So what's the sine of pi? Good. Okay. Then we've got to plug in the 3. So that gives me sine of 3 pi over 2. What's the sine of 3 pi over 2? Good. All right. Then we've got the sine of 4 pi over 2, which is the same as saying 2 pi. Remember, 2 pi is over here at 0. So what's the sine of 2 pi? 0. Okay, I want you to find 5 and 6. Plug in, simplify. Okay, check with your table. See if you guys match answers. Okay, let's check it. So for 5, we would have gotten sine of 5 pi over 2. So remember, you got to count, right? It's pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. 5 pi over 2 takes you back up here again. So what's the sign there? Good. And then this would be, my next round here would be 6 pi over 2 or 3 pi, however you want to think about it. So what's the sign there? 0. Or you hopefully picked up the pattern, right? There was a definite pattern being established there. Okay, let's plot all of that. Okay, so I'm starting with 0, 0. Then I'm going to 1, 1. It doesn't hurt once I make that first plot to put my little arrows so I kind of know which direction I am coming from, because you have to do the arrows in this direction where you start with our lowest t value. Okay. All right, then I'm out 0, 2, out -1, 3, out 0, 4, out 1, 5, and then out 6, 0. And I'm going to go ahead and connect them. I totally missed a dot. and then draw my orientation on there. You don't need a lot of arrows, just a few to let me know where you're going. Okay. Let's take a look at this next section here. Okay. I want you to take about 2 minutes and read that to yourself at least twice. So read it at least twice. Okay, so there are times when we only want to just sketch the rectangular equation, right? This is probably an inverse trig equation right here. If I was going to try to put that in as just an equation into my calculator, okay? So there's times that we do that, and if we're given the parametric equation, we can use a process called eliminating the parameter in order to put it back into rectangular form, which is what we've been doing up to this point. I know we probably haven't heard that word rectangular form before, but that's what our equations have been in up to this point, is rectangular form, okay? I want you to go back and I want you to reread that sentence right there to yourself. It tells us exactly how to do it. So read it to yourself again. Doesn't it sound just like that? Systems of equations with the substitution method. Our system looks a lot, it's not linear. It's not a linear system by any stretch of the imagination, okay? It is a crazy looking equation. But that's all, it's the same concept as what we did with systems of equations by the substitution method. You've got to solve for one of the variables and then take that, plug it into the other equation, okay? We are going to go ahead and try to, let's see what I did with this. Oh, we did that for orientation purposes. Okay. So we're going to try to just graph this with the rectangular version versus doing it with plotting our points, okay? So the first thing I'm going to do is I'm going to try to solve one of these for t. Okay, so I'm looking at these two equations. Actually, let's read the problem. Sketch the curve described by the parametric equations. X equals 1 over the square root of t plus 1, and y equals t over t plus 1, where t is greater than negative 1, by eliminating the parameter and adjusting the domain of the resulting rectangular equation. Okay. So what I want to do is I want to pick either x or y and try to solve for t. Okay. Do you see how the x one only has one t, but the y has two t's? Probably I would try to pick the one that only has one t in it to solve for t. Okay, so I'm going to kind of do that. I'm going to do that work out in the left-hand column. You know, it's not the best place to do work. That's what I'm going to do. So I'm going to start by moving this over to the other side by multiplying. So x square root of t plus 1 equals 1. Okay. Then I am going to go ahead and get this x to the other side. How do I get that x to the other side? Square root it, good. So equals, I don't know why I did this in the column. I just looked at my work again. But it's okay. We got to go in there. We'll start it there. All right. Then how do I undo the square root? Square it, good. So I've got t plus 1 equals 1 over x squared. All I did was distribute my exponent. Okay, I'm almost at t by itself, right? It's an ugly t by itself, but I'm almost there. How do I get that 1 to the other side? Good, so 1 over x squared minus 1. Okay, now that we have what t is, I can take and plug it in for the t's in the other equation. So that's exactly what I am going to do. Okay, so I know that y equals, I'm going to leave some space, and there's a plus 1. Every time I see a t, I'm going to put in 1 over x squared minus 1. I did not do that very well. All right. Our goal here is to try to get this into something simplified that we would recognize enough to be able to graph the equation, like using one of the, either using a line, a parabola, something that we know, one of our standard graphs, okay, if we can. What do you notice is going to happen in the denominator, first of all? Yeah, the ones cancel. Perfect. Okay. I'm going to work with my numerator a little bit at the same time here. Okay. I noticed that I could turn this into 1 over 1. Okay. And if I tried to make a common denominator up here, what would my common denominator be? Good, x squared, which means I don't need to do anything to the first term. It's just a 1. I would be multiplying this by x squared, which means I need to multiply the numerator by x squared. So it'd be minus x squared. And then that denominator on the complex fraction would just stay 1 over x squared. And it's still y equals. I still probably should be writing that part. Okay. Definitely am not recognizing how to graph a complex fraction. So I am going to go ahead and I am going to try to get that out of being a complex fraction. Remember, we take the denominator and we flip it and switch to multiplication. So y equals 1 minus x squared over x squared times x squared over 1. All right, what happens? The x squareds cancel, and I'm just left with y equals 1 minus x squared. We should know what that is. What's the shape? We've got a squared. What's the shape? Yeah, this is a parabola, right? All right, it's a parabola. What do we know about what's the vertex of the parabola? It's 1, right? So it should be up here at 1. What else do we know about the parabola? Is it right side up or upside down? Why is it upside down? It's negative. Perfect. Okay. We could probably put some values in there if we wanted to. If I put a 1 in there, it's just going to give me zeros, whether I put in 1 or negative 1. So it's going to be kind of like that. From there, I could probably just sketch it. Oh, but I have to be careful. Look at my, what's wrong? Oh, the screen just died. Okay, thank you. It's funny because my husband's buddy with the director of technology or whatever, and I told him all of the issues that we've been having. It dies in the middle of class, and I got to keep putting the pin number in. It was like the split second that I looked down. Okay. So that's where so before I actually graph it, there's one other thing I need to take into consideration. Okay. So make sure you got at least that part started. I'll give you a second to get there and reorient yourself to the screen there. Okay, what I have to be careful of is I still have to deal with the domain where my t is greater than 1, right? I really need to know what x value that starts at, okay? So I can't plug -1 into there because that would give me a 0, wouldn't it? But could I plug 0 in? Yeah, and I might have something that's between -1 and 0, and that's okay, but I need to know that I at least kind of where I'm starting a little bit. So I'm going to plug just the 0 into the x. So I'm just going to use my t0 or tx for now. Okay, so I'm plugging in 0. I put 0 into this thing right here. What do we get out of it? 1. Okay, so my x value of 1 is actually where the curve should be starting. I'm not sure that that's... Hold on, let me see what I did before here. It might go backwards from that. Yeah, it does. Okay. So I know that I'm starting kind of here, right? Not that. My curve starts here, and it's going to probably go that direction, but I need to know where... Oh, yeah. That's good. Because if I'm starting here, I should probably go in that direction. It doesn't hurt to... Let's test another value. Let's test 3. Why am I picking on 3? Yeah, then it's 4 in the denominator, right? So that makes it a little bit nicer in the denominator. Okay, so that would be 1/2, right? So out at x equals 1/2. And notice I'm only doing the x value, right? I really don't know what the y value is unless I plugged in. So I'm just saying, okay, I know I go to 1/2. So it looks like I'm on the right track if I am going this direction. But I don't go anything to the right of 1 because the t value started at... The x value started at 1 for the t at 0. Okay. All right. And that's it on that one. Okay, where are we at on time? What time do we get done? We get done at 58. All right. I'm not going to go further than that because I don't want to start derivative unless we're going to be able to have a chance to finish the derivative. Okay. I will find a few problems that I can put out there, but I have something kind of interesting to show you that would probably fill the last 7 minutes of class. So give me just a second.